Hello everyone, welcome to another interesting lecture of control systems. Today's lecture is about route array root characteristics. So in our previous lecture we have seen how to do the stability analysis using the route array. So once we write the route array, then we can do the stability analysis by checking the first terms in the each row or the first column as a whole. And if you have all positive elements in your entire first column, then you call that system to be a stable system. But now what about the roots of the system? So now if we take this route array, so I have written only the first column here because the root characteristics can be set from just the writing, from just taking the first column. So if you see the first column here, it is S5. So I have a fifth order characteristic polynomial. So which means I am having 5 roots because S to the power of 5 gives me 5 roots. And then what about these root characteristics? Good. So if I have to talk about these root characteristics, I can tell you that there is a single sign change. So I have a negative in my first column, which means this is an unstable system. And then I have if you see the sign change, the positive to negative and negative to positive, I have 2 sign changes. So which tells us that my 2 roots are unstable, or they are on the right side of the S-plane, and the remaining 3 roots are on the left half of the S-plane, or they are the stable roots. It's very simple. So look for the sign change, and when you count the number of sign change, and then that many roots you have as your unstable roots, and the rest of the roots are going to be your stable roots. Here you see the 2 roots on the right hand side are the unstable roots, and the 3 roots on your left side are your stable roots. So this way we can we can tell about the root characteristics of the system along with the stability analysis of your system, right? So there are certain other things. So what we have seen 3 cases in our previous examples, right? So we have seen 3 cases. But the first case is when you have a 0 in one of the elements, you use the epsilon. Then we were talking about auxiliary polynomial. So when you have an entire row to be 0, then you are having an auxiliary polynomial. So we will see what happens to the root characteristics when you encounter these cases. So let us take another example which is similar to the previous one, just to make sure that you count these sign changes properly. If you take a look at this, I have from plus to minus, that is a 1 sign change, and then I have again from minus to plus, and that is my second sign change. So I am having 2 sign changes here. And what are the total number of roots? So I have S6, which means it's a 6th order characteristic polynomial, which means I am having 6 roots. And then I can tell that my 2 roots will be on the right side and my 5 roots will be on the left side, and the stable roots are the roots on the left side, and the unstable roots are these 2 roots on my right side. Done. So another example shown here. What happens? So just quickly let's count how many sign changes. So all unstable systems, right? Because when you have a negative sign, when you have the negative in one of the terms, right, on the first column, then your system is no longer stable, right? So we can say it's marginally stable because some of the roots are on the left side, but if we are only interested in stable or unstable. So you have either an all stable system or an all unstable system. So we'll just call this to be an unstable system. Now here, if you see how many sign changes are there, so there are 6 sign changes. So this is a system where you have so many sign changes, which means when you have to do the root characteristics analysis, you cannot stop at S6, because normally if I'm only doing the stability analysis, what will happen is when I come to my S6, I can stop there because I get a negative sign. So my system is unstable. But when I want to do the root analysis, I have to go till S0, right? Go to the lowest and see how many sign changes I have, and that many sign changes indicate those roots are on the unstable side or the right side of your S-plane. Good. So now we are going to do the root analysis for these auxiliary polynomial, because auxiliary polynomial is slightly different because the roots are imaginary. So whenever you get auxiliary polynomial, say like your numerical 3 in your previous class, I can tell that the roots are going to be imaginary, And that is exactly what I'm going to show you here. So how do you do the root analysis for a system, for a system where you get all row elements to be 0, or you have an auxiliary polynomial. So here in this case, my S3 row consists of all zeros, right? So how do we do the root analysis? So here this is a stable system, or it means by my previous notion, all the roots must be on the left side because there is no sign change and all are positive in the first column, right? So all the roots must be on the left hand side, but there is this auxiliary polynomial, so which must be taken care. So when you have an auxiliary polynomial, what we do is we need to quadratic factorize. So we need to factorize this auxiliary polynomial using the quadratic expansion and then find the roots, because that 0 is if you just take a 0, it cannot tell anything about whether it is on the right side or the left side of the plane, right? So we want to do that row analysis, and we are doing it using our traditional quadratic factorization, and I do that by putting my s square equal to x. So I get a second order equation, x square plus 6x plus 8. Then my x is equal to -2 or -4, which means my s is going to be plus or minus j2 and plus or minus 4j. So I have my 4 roots imaginary. See, so these are the 4 roots I have. So I can write, whenever you have an auxiliary equation in 4th order, that is s power 4 plus 6s square plus 8. So which means your 4 roots are going to be imaginary. You can just tell it as it is. But if you get sign change, then you may get real roots also. So it can happen both. But your 4 root characteristics can be set from just the auxiliary polynomial. You can either get imaginary, you can get real, you can get both, right? So we are seeing here, I have 4 roots imaginary, and then I would call this system to be marginally stable, because the imaginary roots are on the which axis? On the y-axis, right? All roots, if they are on the left side, then you have your stable system. But in this case, I have the imaginary roots on the y-axis. They are not completely on the left side. They are on the border, right? They are on the border between the left and the right side. So I call it as a marginally stable system. Okay, so that is for your root, what do you call this, root analysis using the route array. Now we come to another interesting topic. So the next topic of interest to us is our root locus analysis. In root locus analysis, what we do is, it's not more about the stability, but it is just you represent your control system in your graphical form, right? So you represent you take a control system, you do the graphical representation, because there is the saying goes that your an image is 1,000 times more effective than equations. So it says words, but here I'm going to use it as equation. So when I am given a system g of s is equal to k divided by s into s square plus 4s plus 13, then I cannot tell much, right? Maybe I can factorize the poles and I can tell something about the characteristic of the equations or the stability of the systems in terms of the pole analysis. But if I want more, because I can talk about more things about this system, then I definitely need my root locus technique. So the root locus technique allows us to plot this control system behavior on a graph sheet, and then we can do the analysis for that control system by plugging in values. So when I do this completely on the graph sheet, so what I'll take is I'll take this system and represent that on a graphical form, and then I can just pinpoint some values on that graph and see like what happens when this value is this, and what happens to the system when I change this value to this, what will happen to the system. So I can just tell, just plugging in some values, I can get what the other values will be just from that graph. So it is one of the effective ways to analyze the system, and also to make sure that your system is bound and stable, and also it is what its performance is what you intend to be, because you as a designer have certain needs, and you think of your system to work in certain ways, and that is exactly what happens here. So we are going to see the steps for this root locus, and then you will see how do you plot these root locus on a graph sheet. So what was the first step we did was I've just taken that root and I obtained the characteristic equation, and then means I've just factorized it and found the roots. Then the next step is to find the root locus on your real axis. So what I am going to do is, now I have my pole at S1 equal to 0. So that was one of the roots, S1 equal to 0, and the other two roots were imaginary. So I S2 and S3. So now to find the root locus on the real axis, you take which pole, because the real axis is your horizontal axis. So you take a test point on, you take a test point on after this pole S1 equal to 0. Then you see, because if you take it prior, because what we want to do is, I want to see how many poles and zeros are there after this test point. So if I take it prior to S1 equal to 0, if I place it on the right hand side, then I don't have any poles and zeros, so then it is insignificant. So I place it in the left side after this S1 equal to 0. Then I can count the number of poles and zeros, and in this case it is equal to 1, which is an odd number. So I'm only interested in whether it is odd or even. So when it is an odd number, my pole plus, that count is odd number, then I can say that that is included in your real axis. So the root locus on the real axis exists if you have odd number of poles. So that test point which is coming after that is, now if I take that test point to any place to the left side up to infinity, I'm still going to get odd number of poles and zeros on the right side, right, if I count it. So I can say that my root locus is the entire x-axis from S1 equal to 0 till minus infinity. So this is how you do the root locus analysis. And now if I had an even number of poles and zeros, then that is not considered as part of the real axis, or the root locus doesn't exist in that place. So which is something we will see in the coming examples. So for now, let's do this much and we'll move on to step 3. So your step 3 is something about asymptotes and centroids. So what are the asymptotes and centroids? So the centroid is something that tells us about the point, right? So that is like your center of mass of the operation. So your centroid tells us, if your centroid is like say 3, or if your centroid is like 4, then you can say like your ROC, or your the radius of your system is fixed at that 4. So if you change the centroid from 4 to say 40, then your control system working is surrounding that 40. So the centroid tells us the point where that point is like the you can say that is the point of where anchor point you can say, and that is where your control system is going to be located. That is the meaning of centroid. And the formula that we use for finding the centroid is sum of poles minus sum of zeros divided by number of poles minus number of zeros. In this case, we have 3 poles and no zeros, right? And the sum of the poles means the roots, S1 equal to 0, S1 equal to 2 plus 3j, right? So minus 2 plus 3j, so those are the roots. So we are going to do that. And then the angle of asymptotes. So the angle of asymptotes tell us about from that centroid how your system is going. So from that centroid, how your system is behaving. So that is your asymptote. So we are talking about how your angle of asymptotes is just, it says like from centroid, if I have to take my region of operation, so my control system is fixed at that centroid. Then from there, at what angle I can get the optimum performance, then that is going to be your 60 degree here. That is going to be your angle of asymptotes. Good. So that's just simple way of telling. Now the step 4 is breakaway and break-in points. So you need to compute this breakaway and break-in points, but however, realistically, like I'm going to show to you, the root locus plotting doesn't take breakaway and break-in points. So many of the programming softwares I have seen, Scilab, MATLAB, LabVIEW, they all have this root locus plotting, and they normally don't talk about this breakaway point because it is little tedious to compute on pen and paper. But in this case, I'll just show you how we do it. So the breakaway or the break-in point is computed from the characteristic equation. So the characteristic equation for is C of S is equal to G of S divided by 1 plus G of S into H of S. So from that characteristic equation, you get K is equal to minus S into S square plus 4S plus 13. And then you take the differential of this K, that is dk by ds, and then you find what is the value for K. So you have to then. So this, I would normally suggest in your exams, you keep this step 4 as an optional. I don't expect all this, all these students to do this step 4, but and for plotting the root locus, it is never, this is never a question for, they never ask a question on find the break-in point for the system. Right. So they, if they do ask, this is the step, because that is the only precaution. We have as a precaution, we have kept this step here to show you how to find the breakaway and break-in points. Good. So pretty much the root locus is about a lot of parameters you have to find, and then you have to put all these parameters on a graph, and then show that is your system, which you had given as G of S at the beginning of the question. So the question said G of S is equal to K divided by something, and then you are taking asymptotes, centroids, root locus, the real axis, root locus, then breakaway point. Then after this, you're going to see the imaginary point meeting locations, and then after this, you plot it, and then you just say that is your system. And now from this graph, you can infer more than what you could do from that equation. So that should be enough. So now I have taken the dk by ds equal to 0. Then I have found the roots, and the roots have come to be imaginary. And then I have to look for the sign of k, right? What I have to do is I have to plug this S1 and S2 into that equation for k, and then I have to see whether my S1 and S2 are making that k positive and real. So in this case, it's definitely not going to be positive and real, because I have imaginary S1 and S2. So which means there is no breakaway or break-in point for this question. See, so that is the only thing. So like I said, for your root locus, you don't have to compute the breakaway and break-in point. You can do with just all the other steps except step 4. But there is a chance in some of the exams, they ask the question very specifically, find the breakaway point. So in that case, you have to take the characteristic equation, differentiate it, find the roots, and then that is your breakaway and break-in point. So that you take the roots and put it in those equations, right? So just if it is a question for the exam, you can do it. Next, you have your angle of departure and angle of arrival. So the angle of arrival is something that we do for a 0, and then your angle of departure is something we do for the poles. So if you see this angle of departure, so what is these are the x represents the poles of the given question. So S1 equal to 0, and I have two imaginary, two complex poles, right? Two complex conjugate poles. They are perpendicular to each other. Now the angle of departure represents something. So it represents the dashed line. It represents the kind of you can say like a projection between the poles. So my projection between these two poles are shown by the diagonal line on the first, right, between the pole S1 equal to 0 and my first complex conjugate pole. And then the second projection is between this complex conjugate pole. So these are the two projections I can have for my 3-pole system. I'm definitely not looking at the symmetry. So you may ask the question, why a downward diagonal is not considered? Because that would be symmetrical to what I've just done. So we don't consider the symmetry. So we don't use it twice because of the symmetry. So that is one thing to look for. So for this 3-pole system given in the question, your angle of departure, so that is not considered. So what I'm showing there is that symmetry is not considered there. So these are the two projections I can have for the angle of departure. And the angle of departure is calculated as the angle from the horizontal line. So you take the horizontal line and then you project that angle towards that projection line, and that is your angle of projection. So see, the angle of projection theta 1 and theta 2 is shown here. And then from that angle, your final angle of departure is taken to be always a deviation from 180 degree. So that is given as 180 minus theta 1 plus theta 2. So I'm not taking that symmetry line. So just make sure that you have the right projection line. So for the normal questions will be for 3 to 4 pole systems. So you have a 3 systems here, 3 pole system, then you do the projection, you have 2 projection lines, and for a 4 system you have 3 projection lines, which we'll be seeing also in the next numerical. Okay, so now we have to find the angle of departure for the given question. So what I just shared with you is the theory or little bit about the angle of departure, because there is not much in syllabus. When I'm talking about the root locus, I can talk about what these asymptotes are, what about these centroids, and how they are used in analyzing the control systems. I'm trying to keep that lecture as a separate lecture. But for now, the questions mostly are focused on drawing the root locus on the graph or for a given control system, and that is your 12-mark question you see in your exams. And for exams like GATE and SSC service exams, what you see is they ask you to find the centroid for the given control system, find the asymptote angles for the control system, find the breakaway points, and break-in points are very difficult and they are not normally tested, because the entrance exams are mostly, they want you to test on the basic subject knowledge. It's not too much of mathematical computation. So normally we don't see the breakaway and break-in point, but the centroids, asymptotes are probably very much used, and very rarely the angle of departure and angle of arrival. So that is also not very difficult to find. So it involves a lot of trigonometry, right? And if you're very good in this, then that question also should not be a problem for you. So if you see here, how I'm going to compute my theta 1 and theta 2 is I'm drawing both the theta 1 and theta 2 in my same diagram. So my first projection line is the diagonal line, and the second projection line is the vertical line shown in white color. And then I can find my theta 1 because I know that horizontal to be 2 and my vertical to be 3, because I know those roots, right? So I know that to be 2 and 3. Then I can find my theta to be tan inverse 3 by 2, which means my theta 1 is 180 minus tan inverse 3 by 2, and my theta 2 is 90 degree. And then from this I can find my angle of departure. Good. So you get a question very similar to this in your exam, but it will be slightly different. It will be 1 by s into s square plus 3s plus 11. Right. So that is another question I just told you, which was asked in your previous exam. So we are doing one of such type. So these other types you can just follow the same things. Only your answers will be slightly different at each stage, but the steps are the same nevertheless. Now let's go to my step 6. Right. So the last step in our computation is the step 6, which is the meeting point on the imaginary axis. So you need to find where on the imaginary axis your this control system is going to lie. So because your roots are not on the imaginary axis, so you have a pole at S1 equal to 0, and then you have two complex conjugate roots which are not on the imaginary axis, they are on the left side. So this entire system is a stable system. I can tell that because I have a origin pole, and then the complex conjugate is on the left hand side, so which means it is a stable system or a marginally stable system, but definitely not an unstable system. So now to find the crossing point on the imaginary axis, so the procedure is take the characteristic equation and plug in S is equal to j omega, and then take the imaginary terms, equate them to 0, and take the real terms and equate them to 0. So the imaginary terms are written in blue, and I have to take that to be equal to 0, because if a plus ib is equal to 0, if my complex number is a plus ib, and that is equal to 0, the only way that happens is when your a equal to 0 and your b equal to 0. Right, because you cannot compute, you cannot add complex, you cannot add real and complex, you can only write them together. So your a cannot be added with b, and a cannot be multiplied with b, right? So a can be multiplied with b, but not in the a plus ib form. So when I have a plus ib form, which means my a is not adding with b, because b is an imaginary variable and a is a real variable, so which means a equal to 0 and b equal to 0. I know you guys know this much, so so I didn't have to tell all this. So now you have your imaginary, and you are using that imaginary, and you are finding the real axis. Okay, so now this is the MATLAB code for this question. So if you see there, 52 divided by s into s square plus 4s plus 13. So that is the question of the system we have. And this is what your MATLAB gives as a root locus. I've just done it in MATLAB. You can do it in Scilab also. I just show, I want to show for today's lecture I'll use MATLAB, and for tomorrow's lecture, the next lecture, I'll show you how to do this on Scilab. Okay, so these are the poles. One S1 equal to 0 and S2 and S3 are the complex conjugate pole. And you see the meeting point. The meeting point is 1.33. Right, so they are the meeting points on your imaginary axis, and see the root locus on the real axis. So this is what you plot, right? And this is definitely, this is like navigation map for your control system, and this is supposed to tell you a lot of things. Because what I will do is, if I take a value of +5, so I can see like how my system behaves for certain values. If I plug in certain values, I will come to know what will happen to my system. So that is now 3.6 and minus 3.6. Okay, and I can even plot the centroid. So this is at an angle of 33.7, your angle of departure. So I'm just plotting all this. I'm mapping all the things that we have computed so far for you on this question. All right. So now we can do another question. So it is going to be the same things we have seen so far. So that should make things clear for you. So I have a question in this manner: k into s plus 9 divided by s into s square plus 4s plus 11. So I can tell from this question that I have 1 0. I have s plus 9 on the numerator, so that is my 0 term, and then I have a denominator. Good. So I have a denominator which is all poles. I have 3 poles on the denominator, and I have 1 0 in the numerator. So I'm going to do that as the first step. I'm going to locate my poles and zeros, and then I'm going to get it as s equal to 0, and then minus 4 plus or minus root of 16 square, right? 16 minus. So I'm just quadratic factorization. I'm finding the roots to be minus 2 plus or minus j into 2.64. Done. So that is my step 1. So I have my poles P1, P2 and P3. Then I have my 0 at minus 9. So what was step 2? So now we can go to step 2, right? What was the step 2? So just think, so you need to know these steps. Our step 2 was, yes, guess it, what was that? Root locus on your real axis. So we are going to find the root locus on the real axis. So what we are going to do, let me just plot these zeros and poles, and then see which one lies on the real axis, and then after that we are going to take this and then we are going to compute it. So now I have my z1 equal to minus 9, so that is definitely going to come, and I have my p1 equal to 0. So my z1 is minus 9 and this one. So okay, so these are the two things. I'm only interested on the real axis, that is a horizontal axis, and I have only the two, p1 equal to 0 and z1 equal to minus 9 on the real axis. So let us now, what I'm going to do is, I'm going to see, so I'm going to take a point here. So I'm going to take my test points on, these are the two test points. And if I take my test point 1, then to my right side, right, test point 1, and then to that side, so that is my right side, I am going to have how many zeros and poles? I have 1 0 and pole. And to the right of my test point 2, I have 2 zeros and poles. So even and odd. So I've told you for the root locus on real axis, I'm only interested in the odd numbers, which means the root locus lies on the real axis between 0 and minus 9. So after minus 9, it ceases to exist because the test point 2 gives me even number of poles and zeros. So that is not a part of your root locus. All right. So that is how your root locus exists, and that is the same for any question. So you have any number of poles and zeros on the real axis. What you do is you will get more test points. So in this case, you have only 2 test points, but if I had 3 on the real axis, then I would have to take 3 test points, and then wherever the count comes even, that will not be a part of your root locus. And when you have the count to be odd, and then that is your real axis. Good. So this is how we do this. Excellent. So this is the root locus on your real axis. done. So that is for step 2, and now I'm going to my step 3, asymptotes and centroids. So I'm going to compute my asymptotes and centroids. So you can plot these centroids in your graph. So to find the angle of asymptotes and centroids. So what is the formula for your asymptotes? Plus or minus 2 cube plus 1 divided by the number of poles minus 0. And then centroid is sum of poles minus sum of zeros divided by number of poles minus number of zeros. So if you see today, what we have done is we have used a programming software to plot this root locus. So here I can say that they have not taken the angle of asymptotes as it is, right? I'm not seeing that, but still that root locus is a right root locus, because that is what we get. And in most of the practical applications we use MATLAB root locus and we do the analysis of the system. So that is what we use. But let me what I will do is for the next lecture, maybe we are doing one more numerical, that will be the difficult numerical on root locus. Probably I will try to plot using the graph paper. So I'll show you how we can plot all these things on the graph paper. Maybe that should give you a good practice for your exam. So we'll do that. So I've computed my centroid and asymptotes, and after that I'm coming to my angle of departure. Right, so here I have a 0 and I have my 3 poles. So let me see how the projection lines are going to be looking like. So I have 0 here, then I have a pole here, then I have another 2 complex conjugate poles in this manner. So how many projection line I'll be having? Can you tell me? I'll be having 3, right? Because I have now, so I have my first projection line to be this, second projection line shown here, and my third projection line. So the yellow shows the projection line, so which means I'm going to calculate 3 angles from the horizon. So that is my theta 1, theta 2 and theta 3. Theta 1, theta 2 and here theta 2. So then I can now, I know these values, right? So I can, this is my minus 2.64 minus plus 2.64, and then I have that point to be minus 2. I know that this because those are the complex conjugate. And now I can easily write what is my theta 1, theta 2 and theta 3. Theta 1 is equal to 180 minus tan inverse of that vertical is going to be what, 2.64, and my horizontal is going to be 2. Theta 2 is 90 degree, and theta 3 is going to be tan inverse of the horizontal is 2.64 and the vertical is 2.64 and the horizontal is 7. So this is 7 and this is 2. The overall total length is 9. The scaling is totally off. So just don't get confused, but that is what it is. It is 7 appears shorter than 2, but yeah, that is wrong. I'm not very good at drawing these things, but hopefully the meaning is conveyed to you. So angle of departure is 180 minus theta 1 plus theta 2 plus theta 3, and that is gonna come to, so let me compute it. You can use your scientific calculators for these things and solve it in the exam. I'm going to get it as minus 6.4. So most of the marks are for the steps, because no entrance exams are going to ask you to plot the root locus, right? That is why I'm not, I'm just use the program to show, because there is another, drawing the root locus is only a small, it's only for a 2-mark weightage in a 12-mark question, because you have minimum of 5 steps and each step carries 2 marks. So that is, you normally get this for a 12-mark question. So your 10 marks is for the computation, and then your remaining 2 mark is for the graph. So, and no entrance exams, no gate, no SSC exams, no service exams are going to ask you to draw the root locus. The questions are going to be, find the angle of asymptotes for the given control system, find the centroids for the given control system, find the angle of departure for the given control system. So you are, they want you to find these values. They are not going to ask you to draw the root locus. So that's why I've used the program, and probably for the next question, which is going to be the most difficult question. So this is like a medium level difficulty, the second question. The third question is going to be it's going to be a difficult level question. So maybe for that I will plot. I'll use a graph sheet and I'll show you how to do this root locus to scale properly on graph sheet. Good. So the step 5 is to find your meeting point on the imaginary axis, and you do so by plugging in s is equal to j omega. So I have put my s is equal to j omega, and that is going to give you the imaginary and the real parts, and we are going to put the imaginary equal to 0 and the real equal to 0, and then we're going to solve for these points. We're going to find k, and that is going to be my meeting point on the imaginary axis. So these are all testing you mostly on whether you know the process, whether you know the steps, and whether you know to compute, because you have to do a lot of computation, quadratic factorization, finding the roots equation, right? Mostly quadratic factorization. So you have to be very thorough with that. And then yeah, probably you need to know the formulas for computing this meeting point, because I'm not doing the meeting point on g of s. If you look at this, I'm doing the meeting point computation on c of s, and that is obtained by g of s divided by 1 plus g of s into h of s. But h of s is 1, so I've not written it there, so it's not for your confusion, but I should have written h of s there. So it is that formula. So we obtain the c of s, or we take the characteristic equation. So you need to obtain the characteristic equation, and that is obtained only by this g of s divided by 1 plus g of s into h of s formula. And then I'm getting my k to be 8.8 and my omega to be plus or minus 4.4. So your meeting point is plus or minus j 4.4. So that is your meeting point. Okay, now see what I've done here. I have plotted the root locus for the given question using the MATLAB. So this was done using MATLAB, and MATLAB is not a free software. It is a commercial software, but we do have Scilab, which is a free software. So I'll probably use Scilab because I was not able to find a direct function for root locus when I was looking, and maybe I needed more time to write that program. So maybe for the next difficult question, we'll be seeing one more question on root locus, and probably for that I'll be using Scilab and also a normal graph drawing and show you how to do this. So these are the things. I'm labeling the graph. I have 0 at minus 9, I have 3 poles, and then I have root locus on real axis, and then I have my angle of departure to be minus 16.7, or no, it's just 16.4, plus or minus. On the top it's going to be plus, and the bottom it's going to be minus. And then I have my centroid also, right? I can now plot my centroid was at 2.5, so I can put that also. So okay, thank you.